Alright guys, let me know if you have any questions. So I figured out today, as I saw a couple of students in my office hours, there was a typo in my very first lecture where I mentioned that I'll be holding my office hours on Monday and Tuesday, which is not correct, right? So I fixed it, and some of you know already that I hold my office hours on Monday and Wednesday. So those of you who could not pick up the test, right? So the students that I saw in my office hours, they came to pick up the test, and I was busy with lecture preparation, so I could not help them. So yeah, I fixed that error, and I posted an announcement on the Blackboard also regarding that. So hopefully you all know that now I'm holding my office hours on Monday and Wednesday from 12:30 to 2 p.m. NCS. Okay, good. So if you could recollect in the last class, right, we were almost done with recursion. So the tail recursion, probably I told you that it is a little more intense than what we have. So I would request you to just have a flavor of it, like what do we call as a tail recursion, and why is tail recursion good? Because those recursions where you have tail recursion, you can very easily convert this recursive method or a program to a non-recursive one. So what is a tail recursion one? So let's quickly look at that. A method which is defined such that it has one recursive call, and that is the last computation statement, then we call this as the tail recursion one. Now what's the advantage? Well, every tail recursive method can be conveniently, I'll say, right, conveniently written as an equivalent method without recursion, because you can very easily remove or replace that recursive call with a simple iteration or loop. So let's have a look at that. So the factorial version that you're looking at right now is tail recursive. Why? Because if you pay attention to the whole method, then you realize that recursive call we are making as the last computational as the last computation of this method, right? So the whole thing, if you look at, it's based on n. We have the base case. If n is equal to 0, we return 1. We know that 0 factorial is 1. Otherwise, here is the recursive call. We will return n multiplied by factorial of n minus 1. That's where the recursion will kick in. And this is the tail recursion, right? This is the last computation statement in our recursion. So it's extremely convenient, I would say, to simply modify the code over here using an iteration, right? So here we go. What we can do? Well, we will have to use some local variables here, right? Like product. We were not using product in the recursive version, right? Because simply the recursion was doing it for us, although it was taking more memory on the stack, call stack. But here we can have more optimal code by writing it iteratively. So we would need a temporary variable that we are calling as product, initialized to 1. And then this I is for your for loop, right? And easily you can iterate over the value of n and compute the factorial in this variable product and just return that towards the end. So I think we discussed it, right? Towards the end, I remember I did ask you this question, like is recursion efficient, right? So we know, after looking at the example of Fibonacci sequence, we should be convinced that recursion is not efficient. It will take more time, and it will also take more memory. So we should avoid recursion if possible. Now this is one of the examples for which I thought I should cover this one. So fairly simple method that we need to write, which will be printing some number in reverse. So if I pass on the value of n as 5, then it should print 5, then 4, then 3, then 1, and then that's it. So this is reverse print. We want to print the integer in reverse order. So can we do it recursively? Probably yes, right? Very simple. What you will do, we will use the condition if n is greater than 0, then you are going to print the value which is n. You will start with n as being 5 if n is 5, and then after printing it you are doing what? Recursive call with n minus 1. Is it tail recursive? It's written there, right? It's a tail recursion because we have it over here. If I take it here, will that be a tail recursion? Interestingly, there's something called as head recursion as well, right? So that's the reason I was saying, like, it is little intense, right? So better not go into that depth, but yeah, we will think about it, right, in the review and all. But you should have this idea, like whether a function is tail recursive or not. So in this current form, it is tail recursive, but if I take it as the first statement before the print, then that is head recursion. All right, so how can we make it iterative? Fairly simple, so here we have some hint, like how should we proceed. So in the normal, in this place over here, we were using if statement, right, because it is recursive. What we can do is, this if can be replaced by equivalent loop, which we are doing over here, right, while. So we will make use of while. You can make use of for loop also, but while loop seems more natural in this case. And this L is just for us to come up with the corresponding loop. I'll read L as a loop, right? So we are simply writing a loop to work it out. All right, questions? Guys, there is one more very interesting recursive problem, which I would rather leave for you people to walk in the recitation, right? Because there are a lot of interesting topics that we need to discuss. Okay, Tower of Hanoi, it's a very standard problem. All right, I would assume that it will be asked in the interviews also. So I have it there, right? So if you want, you can read it off yourself. Otherwise, I think I have it in the recitation, so you can try that as a problem. What I should do now, if you don't have any question on what we learned in recursion, then I'll take you to the next data structure. Okay, so our next data structure is going to be binary trees. So we should start with the definition. So let's see how can we define the binary tree. So the very first point about this data structure, or the abstract data type that you may call it, is that this is the first data structure which is not linear, it is non-linear, right? So what data structures we have learned till now? We learned about linked lists. One-way linked list is what I did in the class. Probably you did the two-way linked list in the recitation. We learned about stacks, queues. These are all linear, right? We have the notion of sequence, one followed by the other. Now trees, and more so binary trees, are non-linear data structures. From the example you would see, like what do we mean by non-linear. Now question arises, how do we define a binary tree, right? So a binary tree, I mean, you will find a number of definitions, right? I'll request you to stick with the definition that we have over here. So we define a binary tree as either empty, or it will contain, if it is not empty, then it must contain a root node. And when you have a root node, then from that root node we can think of left and right child of the root node, and the left and right childs are also trees, subtrees or binary trees. Okay, so what I should do, let me read it, right, because I did add my own definition to it. So binary tree is either empty, or it contains a root node and its left and right subtrees, and these subtrees are also binary trees. What did you find interesting in this definition? Yep, it is recursive, right? How are we defining it? We are saying, okay, fine, it can be empty. So in fact, this fact that the tree could be empty is serving as a base case for recursion. You agree with me? Right? So we are starting with the base case. We are saying that a tree can be either empty or it can contain a root node and can have left and right subtrees. All right, so as an example, let me start with it, right? Probably it will help us. Let's make a very simple tree with a node A. All right, this could be a tree, right? This is a tree with just one node, that is the root. And in fact, I have nothing over here, that is also a tree. Empty tree. I don't need to draw anything, that is empty. So that is also a tree, but this is a tree with just one node, that is root. So in fact, this root has left child as well as the right child. But the left child and right child is what? Empty. Let me put a box for empty tree. You should not be able to see an empty tree. There is no node over there, right? But in this definition of a tree with just one node, we can think of this node as having left child and the right child being empty. Got it? And you know what? Now let's think about a tree with more nodes, right? A, B, C. Now here we can define this tree as a tree with this node called the root and two childs, left child and the right child. The left child is again a tree with just one node, which is B. Right child is again a binary tree with just one node, which is C, right? So, I mean, I did use the term tree loosely. I should be using binary tree only, right? We can have general trees with more than two nodes, but we will be learning about binary trees only, right? So, binary trees, okay? Questions? Yep.
What is this?
Empty, sorry, yeah. What did I write? Empty tree.
What is it pointing?
Nothing. What is empty set?
So it's nothing.
Nothing there, yeah. There's nothing there, right? So you know what? This definition is recursive. That is what I was highlighting, right? If you read this point, what we have over here, so this definition is recursive. All right, a binary tree is either empty or it contains a root node, like here, and left and right subtrees, left subtree, right subtree, right? And you know, even this guy has a left subtree and a right subtree. Can you see that? We can't because those are empty, right? So this is must for recursive definition, right? Definition of an empty tree. Now the question arises, where do we use binary tree? I say a lot of places, but in encryption seems like it's very important. Databases, I'm pretty sure, and expert systems as well. I would say that, you know, even in compilers, although we don't have that listed, but very soon you'll see that, you know, we can we use trees in compilers as well. Okay, so let's move on and learn some terms related with a tree. So for that we would need an example, right? So here goes a tree. So in this tree we have an important node that we call as root, and root serves the same purpose as the, or similar purpose, I'll say, not the same purpose, like the head of a linked list, right? Linked list is a linear data structure, but for most of the operations that we want to perform on a linked list, we would like to have the reference to the head, because if you give me the reference to the head, then I can traverse the linked list. And similarly for stack, you need the top of the stack. For queue, you need the front and rear. In case of tree, we need just one reference, that is a root. Fine. So after this, after that, let's learn about few other terms. So root is an example of parent, right? So here A is a parent and these two are the childs, and in fact B and C are what? Siblings of each other, right? These two nodes are siblings of each other. Why are they sibling? Because they are sharing the parent. So A is a parent, B is a left child, C is a right child, and recursively you can go down. You can further define D and E as the left and right child of the parent node, which is B. Now D and E, I mean, you can compare D and E, and these two are siblings for the reason that they are sharing the common parent, which is B. Now these nodes like D, E, F and G in that picture are called leaf or leaves. Okay. Similarly in B and C are here leaves. Okay, so what else? Now in this picture we have a left subtree which is defined by the nodes B, D and E, and similarly we have the right subtree which are defined by C, F and G. And if you look at these trees that you have in these are again binary trees, right? You see the recursive definition of binary tree. Okay. Questions? All right, so let's learn about few more terms related with binary trees. Now let's think about two nodes, node X and node Y in a tree. So they can be related, right? So we can have relations between two nodes, like A and B are related, so are A and C. Now it depends like in what direction you are looking at the relationship. So ancestor, let's think about ancestor, like when can we have an ancestor? So we will say that X is an ancestor of a node Y if X is a parent of Y, like in this simple case A is the ancestor of B and A is also the ancestor of C, right? But what I can do is I can add more nodes, A, B, C, D, E, F and G. So in this scenario, if you pick this node like D, then D has B as an ancestor and A as well as the ancestor, right? So ancestor is more general. Ancestor covers not only the parent, it also covers the parent of parent. So X is an ancestor of Y if X is a parent of Y, or X is the ancestor of parent of Y, right? Is that recursive? It's recursive again, right? So as I was saying that, recursion is a bad news for cases like Fibonacci sequence, but a lot of times, you'd start with a recursive solution and then you can modify the recursive to dynamic programming kind of a solution. But for some cases, as you would see here with the trees, they are inherently recursive in nature, right? So we can't throw the recursion out, and you'll find the recursion very useful in understanding this kind of relationship. Okay, it's recursive. Now, can we think of the relationship which is descendant, right? Ancestor and descendant. Like B is a descendant of A, C is a descendant of A. Similarly, D is a descendant of B as well as A. E is a descendant of B as well as A, right? So this kind of relationship. So again, you would find this definition to be recursive. We will say that Y is a descendant of X if, what's the first condition? Can you define the descendant? When will we say, yeah, oh, okay. Yes. Y is a child of X, that's one condition. Or, sorry, yeah. Let's discuss in terms of descendant only, right? Yep. Y is the descendant of the child of X, right? So descendant of child of X, right? D is the descendant of child of, yes, kind of, right? The same thing, but we are looking at a different angle. descendant point of view. So now let's learn about another term, which is the depth of a node. So if we have a node y, then the depth of a node y, like the depth of this guy is c. We can define the depth of all the nodes, right? Depth of this guy, these, all the nodes. So depth of a node y is 0 if y is root, right? So the depth of A is going to be 0. If that's the case, then depth of these two are 1. Depth of these are 2. Okay? Now let me ask you this question. If that's the case, then what is the depth of an empty tree? Okay, so before that I should define you the depth of a tree. So is this thing clear? Depth of root is 0. If you have a node y in a tree, and if y is a root, then its depth would be 0. And the depth of the other nodes is 1 plus the depth of the parent, right? So depth of B is 1 because 0 plus 1, 1. C is 0 plus 1. D is 1 plus 1, 2. E is 1 plus 1, 2, so on and so forth. All right? So you can find the depth of each node in the tree. Now, the depth of the tree. How do we define the depth of a tree? So for depth of a tree, it is defined as the maximum depth. So in this case, what is the depth of this tree? 2, right? So if I add one more, now it will be 3. Got it? Find out the depth of the maximum depth of its leaves, right? So how many leaves do we have now in this tree? There's one more node here, right? 1, 2, 3, 4. So you need to find out the maximum, which is 3 over here. Any question? All right, so now I'll take you back to the empty tree. What should be the depth of an empty tree? How many nodes are there in the empty tree? Let's start from there. 0, right? So what's the depth of that tree? Yep. -1. That's the correct answer, right? Depth of an empty tree is -1, whereas the depth of a tree with just one node, like root, that is 0. It has only one node, which is the which is the root as well as the leaf here, right? How do you define a leaf node of a tree? You are looking at this as a leaf, right? This is not a leaf. So what is unique about the leaf or the leaves of a tree? How do you define a leaf of your tree? Sorry? It has no descendants, right? You wanted to answer, right, at the back? Same thing, right? That has no descendant means, or more, we can make it more precise. We can say it has no left and right child. No descendant, no left and right child. All right. Now the life will get slightly interesting, right? Where the students get a lot confused. A full binary tree. What is a full binary tree, right? So here, if I remove this node, now this is full binary tree, right? So what is a full binary tree? A full binary tree is a tree such that all the leaves have the same depth. There are 1, 2, 3, 4. They all have the same depth. Their depth is 2. That's one condition. And every non-leaf node has 2 children. These are the leaves, right? They are at the same depth. And the other nodes like A, B, C, these are non-leaf nodes. So the non-leaf nodes, they must have 2 children. That is a full tree. All right. I should not use these terms like perfect and all, but yeah, full tree means where you have this kind of a structure. All the leaf nodes have the same depth, and the other nodes, other than the leaf nodes, they will have 2 children, right? Now, what is a complete tree? With complete tree and a full tree, we often get confused. Students do get confused. So what I can do, let me start making a binary tree, right? Just one node. Okay? And after that, is it full tree? No, but this is complete. All right? Is it a full tree? Yes, and complete as well. All right? Is it full? No, it is complete. Not full, but complete. Is it full? No. Is it complete? No. Right? So now let me give you the definition of complete. It's not complete, right? Because the condition of the complete is that, let me show you the definition and then we'll discuss with this example. A complete binary tree is a binary tree such that every level of the tree has the maximum number of nodes possible except the deepest level. Okay? And at the deepest level, the nodes are as left as possible. Okay? So, I said that this is complete, right? This is complete because this is the deepest level. In the deepest level, we don't have 2, we are allowed. At the deepest level, we are allowed, right? And, right, so this I'll consider as complete. How about this? Yeah, this is complete, right? So, I should say that full is more strict condition compared to complete, right? So, in other words, any tree which is full is also complete, but a tree which is complete may not be full. All right, so this is full as well as complete. You can add one more node. Is this full? No, this is not full because how, okay, fine. Is it full or not? So 2-point question, right? First, is it full or not? And second, I'll give you 1 point for correct answer, is it full or not? And the second would be, you'll have to justify why is it not full. Which argument you would use to say that this is not full? Yes. B has only one child. Yeah. That's one argument which I'll take. Not all the leaves are at the same depth, right? So that this is correct too, but I was thinking of that explanation. There are 2 leaves. You see that? C and D. A has the depth of 0, B and C have the depth of 1, and D has the depth of 2. Got it? Is it complete? It is complete, right? Complete because every level has the maximum, like this. Here we can have only 1 node. Here we can have maximum 2, which is the case. Only in the deepest level we don't have maximum nodes, right? So every level of a tree has the maximum number of nodes possible. Every node of the tree has the maximum number of nodes possible except possibly the deepest level. This is the deepest level, right? I don't have complete. And at the deepest level, this is the interesting case, right? Where I think I got some of you people confused. At the deepest level, the nodes are as far left as possible. This is fine, right? So if I add another node here, then it is still complete. But if I add a node over here, then is this complete? No, right? Because if you need it, you should have put it here, as left as possible, right? Okay, questions? All right then, let's look at some example. One tree with just 1 node, another tree with 1, 2, 3, 4, 5, 6, 7, 7 nodes. Is it complete? Is it full? Right? Yes, it is full and complete. How about this one? Is it full? Is it complete? Is it complete? How will you make it complete? Yeah.
You can use the
We won't add, we'll just change this node, right? I'm not allowing you to add any node. Restructure it. Push it to the left, right? Make B as the left child. Okay, fine. Because see, what is wrong here? You have A and then B. It should be as much left as possible for complete, right? So one solution is to have B on the left of A. Got it? One more example. Okay. Yeah, go ahead.
For this one, are you talking about one, like all four trees at once, or are you talking about like each tree individually?
We have the number 1, 2, 3, 4 for 4 different trees, right? We can't think of these as one tree because there should be a connection, right? Are they connected? Is number 1 connected with 2? No, these are 2 separate trees. I can think of this whole slide representing a forest, although forest, I don't know whether we have a data structure like forest, but yeah, these are independent individual trees. And we have one more. Okay, is tree number 4, is that complete? 4 is complete, right? What do you say about tree number 5? Is that full? Is that complete? That is complete, right? How about the most interesting tree? Binary tree, right? Is this a binary tree? This is not a binary tree. Why? Sorry?
It only has one child, so it doesn't have left and right subtrees.
Almost there, right? Yeah.
It's like a linked list, like
Yeah, kind of, right? This child should be either left or right, right? So conceptually, it's not a binary tree. Shift it here or here. Make it left child or a right child. Okay, so don't get tricked if you have a question like this in exam. All right, any questions? Okay. A full binary tree is always a complete binary tree. You agree with me? Agree with this point? Right? Okay, then. The next question. Do the math, okay? What is the number of nodes in a full binary tree? Can we derive an expression for the number of nodes in a full binary tree? Or like in, how many full binary trees can we see here? One? All right, let's just look at this one, right? Look at this one. How many nodes do we have? And can we derive an expression for the number of nodes in a full binary tree? Yep. Yes, go ahead. Good. 2 to the power n plus 1 to the n plus 1. What is n here? What should if it is height, let's use the term d. D is for depth, okay? Let's not introduce one more term which is height. Let's stick with to depth. We learned about depth, right? Depth of a tree is, what is the depth? Do we have the answer? Yep.
Is it a summation from n equals to 0 up to t to the power?
Okay, for the full tree, how many nodes we have on the top at the root? At the root, how many nodes? At that level? Second level? Third level? Then at the level D, how many? Sum it up, which comes out to be 2 to the power D plus 1 minus 1. Does that answer this thing? What is the depth here? 2, right? 2 to the power 3 is 8 minus 1 is 7. 1, 2, 3, 4, 2, 3, 4, 5, 6, and 7. Got it? Right? Cool. Now let's move on to a very interesting concept, which is traversal. Now the question is, before I introduce you to traversal, right, we will look at the implementation. Definitely I'll get to the implementation topic. Now if I give you a tree, right, how will you check whether the tree is properly created or not? Let's think about an assignment. I ask you to write a program which will create a tree, right? And after you have created that tree, say you spend a couple of hours, now you want to check whether the tree got created or not. How will you check that the tree got created? Will the tree look like this? Is the tree being restored like this in your computer? What is it? This is just the conceptual picture, right? Even the linked list, if you go back to the linked list, although conceptually we show the linked list as having nodes and these nodes are connected with the link and all, but in actual they are not stored, conceptually they are connected, right? So as an example, you're doing your homework number 2. So how do you check that the linked list is got created? Are you doing that? Are you checking that? How do you check? You create a linked list, so how to check that the linked list got created? You wrote a method for deleting a node. How to check that the node got deleted? Fairly simple questions, right? What will you do? Traverse the linked list, right? Print the nodes of the linked list. If you're getting the nodes printed in the same sequence, then that means you created your linked list, right? After deletion, again you will print the linked list, and that's how you'll make it. The point is, the next topic that I'm about to introduce to you is called traversal, which is again important, right? If you created a tree, how will you make sure that this tree got created? This is more complex than the linked list. Linked list was linear. You can print the nodes next to each other. Linked list is not linear, right? Okay, fine. If you have a tree like this, right? Your program creates the tree like this, and I'm asking you that, print this tree. Confirm that this tree got created. So in what order you will print these nodes? Is that making sense? Right? In what order? Because it all depends, right? I can print A. After A, what do you want to print? Which node should be printed, right? It's non-linear. A and then? Is my question clear? Right? So we need to learn about the traversal techniques. We can traverse this tree in more than one way, right? So there are 3 important traversal techniques, and you can make use of these traversal techniques to print the tree, okay? So what is pre-order traversal? So in pre-order traversal, look at the algorithm, fairly simple algorithm. What we do, we visit the root. If you have to traverse this tree, if you want to print it out, you start with the root, you visit the root. And then in the second step, what we do? Perform the pre-order traversal of the left subtree. Done with this one in the pre-order traversal. Now you do the pre-order traversal of the left subchild. Pre-order traversal of the left subtree, followed by the pre-order traversal of the right subtree. What is it? What kind of algorithm is this? Recursive again, right? It's just so simple. If I ask you to do a post-order traversal on a really complex tree in exam, which probably I'll do, probably it will take you some time, right? And You may mess it up, right? But I'm saying that as a human being, when you'll be working on the post order traversal, post order is more complex. The easiest is pre order, because I'll give you the trick, like how should you do pre order traversal on a tree which is given to you as a human being. But writing these traversal programs are fairly easy than working on this, right? Why? How? Just because of recursion. It's so simple. We are saying it pre-order because that's how we will prefer the root first. We are preferring the root first, right? So that's the reason it is called pre-order. We would visit the root and then perform the pre-order traversal of the left subtree, perform the pre-order traversal of the right subtree. After this algorithm, I can ask you to think of in order and post order. Probably 50% of you will get it right? Because what we have to do, just change these orders. In pre-order traversal, we first visit the root, then we perform the pre-order traversal of the left subtree, and then we perform the pre-order traversal of the right subtree. Then the next version is in order traversal, right? So in order traversal, what we do, we recursively perform the in order traversal of the left subtree, then you visit the root, followed by the in order traversal of the right subtree. Is it recursive? Yeah, again. Now can you think of the post order traversal? What do we do in post order traversal? In pre order, we started with the root, then did pre order traversal of left subtree, then the pre-order traversal of right subtree. In order traversal, we performed the pre-order traversal of the left subtree, then we visited the root, followed by the in order traversal of the right subtree. In the post order traversal, we do post order traversal of the left subtree, followed by post order traversal of right subtree, and then visiting the root. Okay? Questions? Let's do the traversal. Pre-order traversal. How should we traverse the tree? Okay, in pre-order. What's the algorithm for pre-order? Okay, guys, let me tell you, right? When I teach some topic, I have some bias, right? I believe this is easy. So unless you ask me question, I would continue with my bias that this is easy. Probably you people are not responding, you're just respectful of me. If it is not easy, you need to tell me, right? Can we do it? Yeah, go ahead. Question on previous slide or question on this example? Good. So what I should do, okay, I can do it later. Let me answer your question first of all. Okay, yeah. On the traversal only, right? Oh, okay. I should go further back? Okay. That's a very good question, right? I would say that probably it has to do with the other trees that we'll learn about, which are heap trees, right? So heap trees are complete tree, right? So hold on to this question. You would either have the answer or I'll explain to you, right? Ask this question again. We have some interesting kind of trees like heap trees, max heap and min heap, and those are complete trees, right? So this kind of bias that we have towards the left thing helps us out in that implementation. Okay, yeah, why do we, so good, very good question. So you're saying that in these traversals, why are we preferring the left subtree traversal over the right subtree traversal, right? So for this thing, I'll say this could be just a convention. This could be just a convention, but for your first question, I'm pretty sure that the reason is for implementation of trees like heap trees, right, which are complete trees, max heaps and min heaps. Questions? Good. Okay. So are we ready for traversal? Let's traverse this tree, okay? A, B, C, D, E, F, G. Yes, I have this tree over here, right? So I won't have to draw that again. So how do we do the pre-order traversal, right? We need to, guys, I mean, when we say pre or in order, pre-order or post-order, this refers to the route. All right. In pre-order, we give the highest precedence to route first, and then we recursively do pre-order of the left subtree, followed by pre-order of the right subtree. In case of in-order traversal, we first do in-order traversal of left subtree, then route, followed by the in-order traversal of the right subtree. In post-order traversal, we do post-order traversal of left subtree, post-order traversal of right subtree, and then we do the route. So this pre, in, and post refers to the root node. Is that thing clear? Right? As she asked the question very intelligently, like in all these three cases, if you look at, then we are giving the same order of precedence, right? Like left subtree first and then the right subtree. But this, root, the position of the root is determined by whether we are doing it as pre, in, or post. Right? So the root is taking a position. In the pre-order, we will first do root. In order, we will put in root in between left and right, and in the post order, root comes towards the end. Okay, so let's do the pre-order traversal of this tree, right? So what should be the first node that we will visit? Sorry, good. A, right? That's the root. And then we have to do the pre-order traversal on the left subtree recursively. So which next node you will visit? Pre-order in this guy, right? Now let's do pre-order on this subtree recursively. The next node, which is the next node? Sorry? B. After that, it's left subtree, right? Is this guy over here. Recursively we are doing it, okay? What will we do here? Somebody said that probably, right? D. Okay, so recursion stopped over here, right? Because this is empty. So what would be the next node? Recursion is taking you back. B. And then you will come to the right, which is an E. All right. And again, you are coming back here after recursion, so it will be A. All right. Then now is the turn of this subtree. Pre-order on this subtree, right? So being pre-order, we'll give the precedence to C, being root, and then the pre-order of this guy, which has only one node, that is F, followed by G. Okay, questions? I put B twice, okay, so my bad. EC, I did put A twice, right? Okay, right? The other thing would be interesting. Pre-order is very easy. I'll tell you the trick, right? Why pre-order is so easy. In-order is slightly complex, right? So can someone come up with the in-order traversal of this one? Definitely question on in-order traversal, pre-order traversal, and post-order traversal, because as I said, I consider these as interesting, important, and simple at the same time, right? Conceptual as well. So if I have to do in-order traversal, then which node should I do? And what would be my procedure, right? What should I do? Which node would be the first one? Recursively we are doing it, right? Discard, let's go back, let's come back. Yep. Is it easy? Is it difficult? If it is easy, then I'll completely do it. I mean, we can save time on this. If you need explanation, you need to ask. right? Recursive, yeah.
Why don't we just start from the
Sorry,
Why don't we just start from the left subtree, which is B?
what if we?
Like, are we starting with the left subtree?
Yeah, left subtree, very good.
Yeah, good.
Recursively in order traversal of left subtree, right? So the root will come after the left subtree in order traversal, right? So good. So we will focus on this subtree first, and in this subtree again it's a recursive in order traversal. So what's the left subtree of this tree? Yeah, it would be D. So should D be the first node? All right, because you can't go any further, right? The recursion will stop here. And in order traversal of this node is this tree is very easy, right? DBE. What should be the in order traversal of the node of the tree with only these nodes? DBE. Is that the case, right? So straight away we can write D. In order traversal of this tree would be DBE. Then after that, what we will do, we are done with this subtree, right? What's the next node? A. And once we are done, now we are left with the in order traversal of the right subtree. Is that difficult? Just 3 nodes, right? Which will be F, C and G. Got it? Oh. Post order, please work on it, do the post order, and we'll move to the next slide. Sometimes I'm confused, like what is the reaction of the students? Sometimes students are puzzled, I try to help them out. And sometimes I am puzzled and I don't know how to help the students. Right? So guys, please, again my request, be a little disciplined in the class. Right? Yep. In post order, see, it has to go recursively. In order, ultimately, yes, you will go, right? Recursion will take you down to the leftmost subtree, right? And that's how you would work.
So do we always start the root from the root?
Yeah, we will always start from the root because the pre-order is defined that way, right? Your tree could have just one node. If the tree has just one node, then that's the leaf also, that's the root also. So yeah, should we work on post order? So tell me. So guys, if I could put the number here, right? This is say 1, this is 2, this is 3. In pre-order, we gave the preference to 1 and then 2 and 3. In post order, it is going to be 1, 2 and 3. See that? Right? Let's recursively do pre or post order traversal of this left subtree marked as 1. Then we will do post order traversal of this subtree marked as 2 followed by A. Good? So let's apply post order traversal to the subtree marked as 1. What is it? Is that difficult? D, then E, B, right? Root will come out towards the end. D, E and B. And after that, should we go to A? No. Let's do a recursive post order traversal of the right subtree. How to do that? Same way, right? F, G, C. We are done with left subtree post order traversal. We are done with right subtree traversal. Now we are left with root. Good? So D, E, B, F, G, C and A. Again, I'm thinking that these are simple, right? So unless you say these are not, I assume these are. Okay, so let me give you a trick for pre-order traversal. And trick is only for pre-order traversal, right? So the trick goes like this. In exam, right, use your pencil and trace like this: A, B, D, F, G, and then go in C, E, H, I. That's the pre-order traversal. For pre-order traversal, simply trace through it, right? So A, B, D, F, G, C, E, H, I. Got it? Only for pre-order we have this trick. For other, you will have to apply the algorithm. Okay? So for in order, yeah, can someone tell me what is the in order thing? In order traversal for this? I should leave it on you people to figure out, right? Or if it is difficult, let me know. Seems like you people are applying, so I should not rush. Yeah, good. Sorry. In order, right? In order, what I'll do, this is my root, that's my left subtree, and this is my right subtree. Okay? So let's do in order traversal of left subtree. And in the left subtree, do I have anything on the left? No, right? So I will start with B, right? B, and then after that I will have to do in order traversal of this subtree with F, D, and G, right? Can I do in order F, D, and G, right? F, D, G, getting it, right? And then A, all right? And now left in order traversal of the right subtree, where for this guy I don't have any left subtree, so I can take it, okay, E, and I'll do in order traversal of the right subtree for this one, which is I, H, and then C. Kind of, I mean, I should not be calling it math, but yes, I hope I got it correct, right? And similarly, you can do the post order traversal also. And for post order traversal, right, it will start with F, G, D, right, and then B, and here it will be I, H, E, C, A. Simply apply these algorithms, and for these kind of problems you just need to remember the concept, and if you remember the concept you can write these algorithms as well, right? Simple algorithm is easy, even the program is not that complex, just remember the recursion, and probably after that you would love the recursion. How about this? What kind of tree is this now, right? Now if you're looking at this tree, then there are, okay, fine, let me ask you, what is interesting that you found in this tree? Do we have some interesting property of this tree, right? This is different from the previous trees that we saw, right? Yeah. Leaves are, which are operands, right? Leaves are operands, and how about non-leaves? Non-leaves are operator, and this tree is called the expression tree. And I said that trees are important in compilers. So if you happen to learn about compilers, you would encounter these expression trees, right, which determines like in what order the expressions are computed. All right. So can we do pre-order, in-order, and post-order traversal on this? Just do the pre-order and tell me how the pre-order can be done. We know the trick for pre-order, right, which goes like this. Okay, then this guy, and then this. Okay, so which will be star plus A, B, star plus A, B, division C and D. Got it? So what kind of expression is this? Have we learned this kind of expression? Sorry? Prefix. Yes, right? It is prefix. And if I do in order traversal, what will I get? Infix notation. And if I go do post order traversal, I'll get the postfix, right? So you see everything is connected, right? So if you are given an expression tree, you can do different kind of traversals to get different notations, right? If you do a post order traversal, you'll get the postfix notation. In order traversal, you'll get simple infix notation. Now the next question is interesting, right? But before, the next slide is interesting, but let me ask you a question before I take you to the next slide. Guys, if I give you the traversal result, right? Say the pre-order traversal is ABC. Now tell me the tree that corresponds to the pre-order traversal ABC. Is that question clear? There is a tree with 3 nodes, A, B, and C. A, B, and C. These are 3 nodes, and I'm just telling you that this is the pre-order traversal. Now tell me, can we draw only one tree with this pre-order traversal? Is there a unique tree that will have this pre-order traversal? Or in other words, my question is, can we have more than one trees with the same pre-order traversal? Can you suggest me, like, if this is the pre-order traversal, then what kind of structures we can draw for this one? Yes? A, B, and C. That is one possibility. Can we have another possibility? Yes? You see that? Right? So the traversal are not unique. Look at this. In fact, we have 3 trees. Are they trees? What you have on the left hand side, is that a tree? Right? That is a tree, but it is called degenerated tree, right? Because it's just like a linked list, right? We don't have any right node, okay? Which is very inefficient tree. And same is the case with the tree that you have on the right hand side. Yeah.
So the first one, it is a tree, but not a binary.
It is tree. It is binary tree, but it is degenerated binary tree. Okay. It is binary tree because you know A has a left child, but no right child. Right child is null. B again has a left child, but no right child. Right? So you can have right child as null or left child as null. So all these 3 are in fact binary trees. Got it? Because look at the direction, sense of direction. You should have left or right child. And interestingly, in all these 3 trees that you're looking at, their pre-order traversal is A, B, and C only. This is not unique to pre-order traversal. Same thing you can try with the post-order and in-order also. Now, any question, guys? Okay, so if you get these questions and you want to do well in CSC 214, I would say you should target to get 100%. Simple math, right? I consider that as math. Simple logic, simple concepts. Direct questions. Implementation of a binary tree. From here, your life will get slightly complex, but if you are following along, if you're implementing, definitely I would assume you'll do better. So now the question arises, how can we implement a binary tree? Now let me ask you your thoughts, right? If you have to implement a binary tree, what kind of data structure you'll use, right? We need some basic data structure. Even for stack, if you remember, we relied on some data structures that we had previously learned. For queue also, we did use some existing data structures, right? For both these data structures like queues and stack, we use linked list as well as an array. Okay, so my question to you is, for tree, what do you think? What should we use? Yes, a variant of linked list, right? Because linked list is more flexible. Can anyone think of a tree implementation where we can use a simple array? The answer is yes, right? As one of the student asked, right? Like, why are we biased towards left? So yeah, the heap trees, max heaps and all, they are complete trees, and those are implemented using an array, right? So array is a very simple data structure, but still it's very useful. Okay, so let's not worry about heap trees right now. For this implementation, we will look at the linked list variant. You can use an array to store the nodes. We have it. The first point is kind of hinting us towards that only. If your tree is complete binary tree, then you can use an array. But the way we have seen our binary trees, we want to learn about more general binary trees, right? We don't want to have this restriction that the tree should be complete. In that case, we should go with flexible data structure that is going to be a singly linked list. We can use a variant of singly linked list where each data element is stored in a node with links to left and right children. This guy has the link to left child, right child, this node as well. All the nodes that you have in the tree, they should have the provision of linking that node to the left as well as right. Okay, question? All right, so in this variant of linked list that we will use to implement the binary tree, we will have a reference to a node called root. So instead of a head reference, we will use a root reference to the root of the node of the tree. So we can think of a binary tree like this, right? So the arrow we have taken or borrowed from the linked list, right? All the nodes in the linked list, they were connected with one arrow to show the link. Now here we are looking at the binary tree, therefore for each node we will be using two arrows. One arrow on the left hand side to link it to its left subtree, and the other one to the right subtree or the right node. All right, questions? If not, then let's look at the node, right? For any linked list implementation or variant, we need to think about the class that would define the node, right? So let's think about the class which will define the node for this tree. We are calling that a binary tree node, BT node. So you define public class BT node, and in that class we will have data field, right? Because tree is useless unless you store some data there, and we are creating a binary tree for integer data. That's the reason the data field is going to be int. Then after that we will make use of two references to two reference data fields, like left. Look at it, right? Its type is the same as the type of the class, and similarly you will have the right. Okay, and that is the definition of, the data fields. I would say these are the three data fields that we would need. Data for the information part, left is the reference to the left node, right is the reference to the right node. All right, and this again is an example of self-referencing class, right, because it references to itself. And in fact this class definition is recursive in structure, right? So in fact all the classes that we use to define a linked list, they had this recursive structure, right? So here we have two recursion kind of structure. You can think of left as well as right are in fact the data fields of the same type as the class itself. Okay, then we can think of other methods. So can you tell me how the constructor look like? Can we think in advance about the constructor? What do we need in our constructor? What will this constructor do? What should be the purpose of the constructor of this class? To create a binary tree node. And when you're creating a binary tree node, then what values do we need to in that node that you create, right? Yep. data field, right? So that's the value that we'll get. And what will you do with the left and right? Do we need some value for left and right also? No, we'll leave those as null, and we'll create a node and we'll fix it somewhere, right? So let's not change what we have learned. Okay, so here goes the constructor, and for constructor, as you people suggested, we would accept a value for that node. Tree node must have the data. That's what we are getting in this parameter, and then data field would be initialized with this. You leave left as null, right as null. Good. Then you can think of different getters and setter methods. So get data you can write, right? Simple one line. Set data you can write. Get left, set left, get right, set right. Good. Questions? Implement these things, right? Because it will be a waste of time to discuss these implementation. I'll assume that you can do it and try it out, right? Write a program, and these things you can use. You can fill in the blanks, right, for these methods. In order, right? Now let's think about in order traversal implementation. Okay, so for in order traversal on this node, what we do, if left is not equal to null, then what will you do? Left dot in order. Okay, system dot out dot println data, that's when you are visiting the node, and if right is not equal to null, right dot in order. Is it difficult? No, right? That's what I said. Because of the recursion, it is so easy. In order traversal, we need to remember like what is how do we traverse, right? So in order traversal, we recursively do left tree sub in order traversal, then we visit the root, and after that we do recursively in order traversal of the right subtree. The same thing has been implemented here. So before you attempt to do the in order traversal of the left subtree, you want to check whether the left subtree is empty or not, right? So you will check if left is not null, then let's do in order traversal on the left. So that you'll do like left dot in order. So that will take care of the recursive in order traversal of left subtree. Okay, and your being in order, your root will be sitting in between these two. So you print the data part of the root, and in this part here you will check for condition only if your right subtree is not empty. You can check that if right is not null, then you'll do right dot in order, which is recursive in order traversal of the right subtree. Okay, questions? If I ask you to write the implementation of pre-order and post-order, can you do that on the basis of what we have here? All right, how will our pre-order be different from this one? Yes? Oh, very good. Yeah, that's what we have to do. Let's move this box. I'll have to put a box over here, right, to the top, because we need to give the priority to the root, then recursively left and recursively right. And in the post order, take that print to the bottom. Pre-order is here, system.out.println data, as you said, and if left is not equal to null, then left dot pre-order. If right is not equal to null, right dot pre-order. We don't have post order in the lecture slide, probably for the reason that you can work it out. Okay, questions? I have few minutes left. So I'll take you to the next lecture slides, and here we go. So we did look at general binary tree, right? It is still very general. We can impose more rules on the binary tree, right? So let's see, let's think about a version of a binary tree which is called binary search tree, right? So we will now attempt to implement binary search tree. What did we implement? Do you remember what was that implementation for? We just finished discussing some implementation, right? What was that for? Yep. A node, right? So we learned about writing a node structure which we can use to create more specialized kind of trees, right? So let's look at a class of binary trees which are called binary search trees. Extremely important for this course as well as for your interviews. It's very common, right? Interviewers, they ask a lot of questions on binary search tree. And in fact, more advanced trees like B trees, B plus trees, which you might learn in databases, they are variant of binary search tree only. They are more complex. In binary search tree, we have two childs. In B trees and B plus trees, you can have more than two child. Okay. So binary search tree has a property which is like this. All the leaf nodes, all the nodes in the left subtree are less than root. Okay. And all the nodes in the right subtree are greater than the root. So in these trees, we don't have anything like that, right? I mean, yeah, we don't have anything like that, right? The question is, can we compare these nodes? Probably not. But if I put some numbers here, and the numbers are such that these conditions are satisfied, what are the conditions? Conditions are that all the nodes in the left subtree are less than the root, and all the nodes on the right subtree are greater than the node, then that will become a binary search tree. Questions? So what I should do, let me show you a binary search tree if I have